Welcome back to bonding. In part 3 of this unit, we are going to be discussing Lewis structures in great detail for covalent bonding, including resonance structures and formal charges. Let's go. Right, so I have some rules for writing Lewis structures, and really the first 5 are rules and the rest are more like guidelines. So we're going to go through a couple at a time, then we're going to do some examples, and we're going to go through a couple more rules. Notice in your notes packet, all the rules are on the first 2 pages, and then after that, there's spaces for all the examples. So you're kind of going to be flipping back and forth, but at the end, all of your examples will all be bundled together. So here we go. First of all, rule number 1, add up all the valence electrons, including any charges. And so what that means is if there's a -1, that means you're gaining an electron, so you should have 1 more. Or +2 means you're losing 2, so you should have 2 less. Place the unique atom in the central location. This is going to tend to be the atom with the lower electronegativity, but it won't always be. And place the other atoms around it so that you can have a skeleton structure. And then place a single bond between the central atom and each of the other atoms. Give all of them an octet if needed. So group 2 and 13 don't really need an octet, so they don't need 8 electrons. Remember, hydrogen also does not need 8 electrons. Count the number of electrons placed in your structure. If it's the same as step 1, you are done. Okay, so we're going to try some examples from rules 1 through 3. Flip to the example page on your notes. Let's start with water. Step 1 is add up the number of valence electrons. Hydrogen's in group 1, so that's 1 valence electron. There's 2 hydrogens, so that's another valence electron. And oxygen's in group 16, so that's 6 valence electrons. A total of 8 valence electrons. Then the skeleton structure has the unique atom in the center with the other atoms on the outside of it, and give everyone a single bond. Next rule is give everyone an octet. Hydrogen does not need an octet, so it's good. Oxygen does, so I'm adding extra electrons. The bond here counts as 2 electrons, and the bond there counts as 2 electrons. So with those 2 electrons plus the 4 extra electrons and the 2 lone pairs, that's an octet for oxygen. So now all we're going to do is count up what we have, and if it matches, we're good. We have 2, 4, 6, 8. 8 equals 8. Check. This reaction or this molecule is complete. So that ended up looking like this. All right, so let's do HCl. Hydrogen is in group 1, 1 valence electron. Chlorine is in group 17, 7 valence electrons, which is a total of 8 valence electrons. There is not a unique atom, so there is no central atom, so we're just going to place a line between the 2 atoms. Hydrogen is going to get an octet. Chlorine will not get an octet. I think I said that backwards. Chlorine is going to get an octet. Hydrogen will not get an octet. So we're going to add extra dots around the chlorine to give it 8 total. Remember that the line counts as 2. So that's 2, 4, 6, 8 electrons. 8 equals 8 electrons. Check. This one's good. Let's look at NF3. Nitrogen's in group 15. It has 5 valence electrons. Fluorine is in group 17. It has 7 valence electrons. There's 3 of them, so that's 26 electrons total. We're going to put the unique atom in the center and the others around it, connected with a single bond. Everyone in this case is going to get an octet. We don't have any hydrogens or anybody in group 2 or 13. Which means I'm going to add 2 extra dots to the nitrogen, because the 3 bonds count as 6 electrons for nitrogen, so that 1 lone pair will complete the octet. Now I'm going to count what I have and see if it matches. We have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Equals 26. Check. This is good. All right, rule 4. If you have too many electrons in your structure, remove a lone pair from two adjacent atoms, that's atoms that are next to each other, so 4 electrons total, and add an extra bond between those two atoms to form a double bond. Removing 2 additional pairs of adjacent electrons can form a triple bond. So again, flip over to your example page. We've got O3. First step is count the valence electrons. Oxygen is in group 16, so it has 6 valence electrons. There are 3 of them, so that's a total of 18 valence electrons. There is no unique atom, so we're just going to make a chain of 3 O's and give everybody an octet. Now let's count the electrons and see if we're done. We have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. 20. We're only supposed to have 18. This is going to be a problem. Let me get rid of my red lines here. Whoa, let me start over so I can get rid of my red lines. So anyway, that picture as it is has 20 electrons. So what we're going to do is remove a lone pair from 2 adjacent atoms. It doesn't really matter. Let's pick the oxygen in the middle and on the left-hand side. You could also pick the oxygen in the middle on the right-hand side. In place of those 2 pairs, we're going to make 1 pair. In place of those 2 pairs, we're going to make 1 pair. Now let's count. 2, 4, 6, 8, 10, 12, 14, 16, 18 equals 18. Check. So that was O. Just to make sure you've got a pretty picture. All right, let's look at CO. For CO, carbon has 4 valence electrons. It's in group 14. Oxygen has 6 valence electrons. It's in group 16. There should be 10 electrons when all is said and done. So we have C, line O, with an octet for both of them. Neither of those atoms is special. So now let's count what we have. We've got 2, 4, 6, 8, 10, 12, 14. 14. That's a problem because I'm only supposed to have 10. So what I'm going to do is remove a pair, 2 pairs from 2 adjacent electrons. 2 pairs total. So I'm going to pick 2 adjacent atoms, sorry. I'm going to pick 1 from carbon, 1 from oxygen, and replace those with a bond. Now let's count. 2, 4, 6, 8, 10, 12. That's still too many. So now I'm going to remove another set of pairs from 2 adjacent atoms, which happen to be the only 2 atoms in this case. Let's take off the bottom ones and replace them with a line. And now count again. 2, 4, 6, 8, 10. Hey, 10! We got it! All right, let's look at CO2. Carbon has 4 valence electrons in group 14. Oxygen has 6 valence electrons, and there's 2 of them, which is a total of 16 electrons. Put carbon in the center because it is the unique atom, and the other guys around the outside. Give everybody an octet, and count what you have. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Uh-oh, supposed to have only 16. So, let me get rid of my arrows. And then we're going to remove a pair from 2 adjacent atoms. So, the carbon and 1 of the oxygens. Doesn't really matter which one at this point. Now if we count 2, 4, 6, 8, 10, 12, 14, 16, 18. Oh dear, that's still too many. So now I'm going to remove another 2 pairs from another 2 adjacent electrons. I could take 1 from carbon and again the oxygen on the left, or I could take 1 from carbon and the oxygen on the right. For the sake of symmetry, let's do one from the right. But later on when we talk about formal charges, we'll get to which one would be better. Now let's count again. 2, 4, 6, 8, 10, 12, 14, 16. Hey, 16! Check. Our structure is beautiful. Rule 5. If you have too few electrons in your structure, add extra electrons to the central atom to give it an expanded octet. The central atom may have 10 or even 12 electrons around it. This only happens for central atoms in periods 3 through 6, as their d electrons contribute to bonding. So atoms in period 2 don't have any d electrons, so they will never form expanded octets. So here we are with BrF3. That's our first example. Flip back to your examples page. Br has 7. Fluorine also has 7, and there's 3 of them. That's a total of 28 electrons. We're going to put the unique atom in the center and the other atoms around it. And then give everyone an octet. There's nobody special here that doesn't need an octet. And then count what you have. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, and 26. Almost missed one. 26? I'm supposed to have 28. That means I'm going to need 2 more electrons. So those 2 more electrons are going to go on the central atom. Doesn't really matter where, just wherever you have space. And when I do that, I like to kind of circle those lone pairs to remind myself, to let everybody know that those electrons are a little bit awkward because bromine has greater than an octet. So make sure that you do that just to kind of set it apart. That's your BrF3. Let's try XeF4. Xenon is a noble gas. It has 8 valence electrons. Fluorine's in group 17, so it has 7, and there's 4 of them. 28 plus 8 is 36 electrons total. That's what we should be getting. So we'll start with Xe and put the fluorines around it. Then give everybody an octet. I know those I'll put those up there so you can see them better. Okay, so as far as valence electrons, notice that this whole group there has 8. So that's 8, 16 here, 24 there, 32 here. 32 is not 36. I need 4 more electrons. So I'm going to put those 4 more electrons as 2 pairs on the xenon and circle them to kind of show them apart so that now I have 36 electrons. PCl5, phosphorus has 5, plus 5 times chlorine, so 5 times 7, is 35 plus 5, which is 40 electrons. So we're going to put phosphorus in the center and Cl on the outside. There are 5 Cls. Well, that doesn't look like Cls. Everybody is going to get an octet. Dots everywhere. And now we're going to count what we have. This is 8, 16, 24, 32, 40. It's 40 all by itself. This counts as an expanded octet because their phosphorus is connected to 5 different chlorines. So phosphorus here has 10 electrons around it. Even though we're not adding extra lone pairs, it's still an expanded octet. The same with the next one. Let's look at SF6. Sulfur's in group 16, it has 6 valence electrons. Fluorine's in group 17, that's 6 times 7, so that ends up being 6 times 8, which is 48 electrons. We're going to put the sulfur in the center and the fluorines on the outside. Make sure you leave enough room for 6 fluorines. This is going to be a crowded structure. Make sure you leave enough room for all your dots. You are not allowed to skip the dots, even though it's annoying to have to draw this many little dots. Make sure you include them. So, counting up our electrons, we have 8, 16, 24, 32, 40, 48, and 48. Check! That's a beautiful structure of SF6. Next rule. And now, starting here, the rules are more like guidelines rather than rule like how to do. This is more just how to arrange the atoms. So, in most oxyanions, that's an anion, a negative ion that has oxygen in it. Oxygens are bonded to the other element, not to each other. So if I have ClO4, that is not O, 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 Cl, O. No, it is oxygens all bonded to the chlorine. That might seem obvious, but we just want to make sure we say the oxygens are not in a big long chain. So we're going to count up the valence electrons. Chlorine has 7, plus 4 times 6 for oxygen, plus 1 more because of this negative sign. That means we're gaining an electron from what we should have had. So 4 times 6 is 24, plus 7 plus 1 is 24 plus 8, 32. 32 electrons. Okay, now we're going to draw a Cl with 4 O's around it. And give everyone an octet. And then we're going to count. That's 8, 16, 24, 32, which is totally correct, and we're very good. The only thing here that we need to add, because this is an anion, it has an overall charge. We need to show that the molecule has an overall charge by putting the molecule in a bracket and putting a big negative sign next to it, saying overall this thing will have a -1 charge. For SO3 minus 2, we have 6 plus 3 times 6, that's 18 plus 6 is 24, plus 2 more, so 18 plus 6 is 24, plus another 2 is 26 electrons. We're going to put sulfur in the center and have the oxygens on the outside. Give everyone an octet, including sulfur. Count what you have, 8, 16, 24, 25, 26. Everything's good, all looking well. What we need to remember to include here is the overall -2 charge. Okay, next rule. In most oxyacids, that is an acid, it means it starts with H, that has oxygen in it. In other words, not a binary acid. The acidic hydrogens are bonded to oxygen, not to the other element. So in HClO, it is not HClO. Tricky. In HClO, the H is bonded to the O, not the Cl, so it actually ends up looking like that. In HNO2, it's not H with N, it's actually H with O, then an N. In H2SO3, these 2 hydrogens are bonded to 2 of these oxygens, not to the sulfur. In H3PO4, these 3 hydrogens are bonded to oxygens, not to the phosphorus. Okay, so let's start by counting our valence electrons. Hydrogen is 1, plus 7 for chlorine, plus 6 for oxygen. 8 and 6 is 14. Now that I've got the structure, let's make sure everyone who wants one has an octet. Does not include hydrogen. Now we're going to count. We have, let's see, 2, 4, 6, 8, 10, 12, 14 electrons. Hey, 14 electrons, beautiful. I love it when my structures end up just like they should. Let's try the next example. HClO4, that's 1, plus 7, plus 4 times 6. 24 plus 8 is 32 electrons. In HClO4, Cl is the central atom. The O's are bonded to the Cl, And the H is bonded to one of the O's. It actually doesn't matter which one, just one of the oxygens. Now everybody gets an octet, except for hydrogen. He doesn't need that many. And now we're going to count up what we have. We have 8, 16, 24, 26, 28, 30, 32. Yay, that's exactly what we needed, 32 electrons. So there is your oxy acid. All right, next guideline. Within molecules or polyatomic ions, oxygen normally forms no more than 2 covalent bonds. Hydrogen is considered terminal, which means it comes at the end of a row, not in between. And if they're not the central atom, halogens are also terminal. So you're not going to see a Cl in the middle of a line. You'll see Cls only at the end, unless they're in the center. Okay, let's try the next one. H2, that's hydrogen plus sulfur, that's 6, plus 3 times oxygen, that's another 6. 18 and 6 is 24, plus another 2, 26 electrons. Sulfur is the unique atom that goes in the center. The oxygens go around it. And hydrogen picks one oxygen to go on that one. Oh, there's 2 hydrogens. Let's pick 2 oxygens to go around it. Now we're going to draw the octet for everyone who needs one. And now we're going to count. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28. Man, we're only supposed to have 26 electrons. 28 is too many. Do you remember what you're supposed to do when you have too many electrons? We're going to have to get rid of some. We're going to pick adjacent atoms to get rid of them. So we'll start with sulfur and pick one of its adjacent atoms. I'm actually going to pick the oxygen that doesn't have a hydrogen on it, so that the other oxygens can have no more than 2 bonds. So I don't want to put a double bond right there, right here, because that gives oxygen 3 bonds, and oxygen does not want to have 3 bonds. It really only wants to have a maximum of 2. So instead, there it is. Now if we count again, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Hey, 24. H2SO3. H3PO4. 3 plus 5 plus 4 times 6. That's 24 plus 8 is 32 electrons. The phosphorus is in the center. The oxygens are around it. The hydrogens, pick 3 different oxygens. We are not going to put 2 hydrogens on a single oxygen because that would give that single oxygen 3 bonds. An oxygen normally forms no more than 2. Everybody gets an octet. We are crazy with the lone pairs here. Now we count. We have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Hey, it totally matches. 32 electrons, no double bonds necessary. Next rule. Okay, so on this next one, only a few atoms can form multiple bonds. The only common cases involve carbon, nitrogen, oxygen, sulfur. If it's not one of those 4, you're not going to see multiple double or triple bonds at all. So we have AlCl3. 3 electrons plus 3 times 7. 21 plus 3 is 24 electrons. Al in the center, Cl around the outside. Give everyone an octet. Count my electrons. This is 8, 16, 24, 26. 26, I'm going to have to get rid of 2 on aluminum and get rid of 2 on a chlorine and cause a double bond to happen. Let's try that. I'm going to get rid of here and get rid of there and make a double bond. Oh, this is really a bad idea, because now we're giving aluminum 4 bonds instead of just 3, and a double bond. Well, that seems a little odd. Oh wait, remember at the beginning, group 13 does not need an octet. We did not need to initially give aluminum that lone pair, because aluminum does not have to have an octet. So once you get there and you have too many, instead of giving aluminum a double bond, just take away those electrons that don't need to be there in the first place. So if we have BeCl2, that's 2 plus 7 plus 7, which is 16 electrons. Be in the center, Cl, Cl, give everyone an octet. Count them up, 8, 16, 20, 22. That's too many, so I think I should take away adjacent electrons, just like when I did CO2. I took away these electrons and I made a bond there. Then I took away these electrons and I made a bond there. That looks just like CO2 did. Problem is, Be is not carbon, nitrogen, oxygen, sulfur. Be is not going to get double bonds. Also, Be does not really need an octet in the first place. So when you're drawing this and you're giving everyone an octet, make sure chlorine gets one, but beryllium doesn't need to have one. So if we're counting up the valence electrons, we have 8 and 16, which matches with 16. Check. Okay, we're actually going to stop this video here and pick up again resonance structures and formal charges on the next one, bonding part 3B. Hope to see you there.